Okay, so in the last class we talked about the like how the multiple linear regression. Essentially, this is to solve this in the big data problem. It's not that hard, okay? But I do want to there's like one or two points I want to on to share to the class that you may not recognize before, but it's actually pretty useful techniques. So I'm not going to repeat the multilinear regression like the assumptions. I just directly jump to the to its form. So sharing. Today there's going to be some writing. I have a line here just to remind me I cannot go beyond that line. So the problem is y equal to x beta, right? Plus epsilon. I just want to I mean if you are familiar with this is a linear regression on this matrix form, this is probably easy for you, but I just want to write it out just to so everybody knows. The problem here is your y is n by 1, the vector. Your x is n by p, so-called design matrix. Your beta is a p by 1, the coefficient vector. So epsilon would be n by 1, the arrow term. So in the usual way, we assume this epsilon is follow multivariate normal with mean 0, variance sigma, and the covariant structure will just be the identity. So sigma, so epsilon is going to follow the normal with mean 0, and variance is a sigma times in, right? So this just means for the arrows they are just IID, right? Normal for normal distribution. Now, if you want to estimate for the beta, then what you do is just well in here we if you just want to get in the estimation, you don't actually need the normal assumption. But if you want to get the variance, you would need normal. So just very briefly, okay, to show those if you are not familiar with the linear regression, or particularly in the matrix form, how it looks like. So in order to get estimation, you typically just minimize. You want to minimize the so-called the sum of square arrows. So respect to beta. So SSE, this is going to be equal to. So this is minimized with respect to beta. Basically, is y minus x beta transpose y minus x beta. Okay. So what do you do here? This is essentially this is equal to epsilon transpose epsilon, right? Which is equal to summation I from 1 to n of epsilon I squared. This is just basically this is a sum of square of the arrows, right? So then when you have in this is when you have in this term, what you just do is basically that's minimize with like beta. We have y transpose y minus 2 x transpose beta transpose y, or you can write it another way. Y transpose x beta plus x transpose beta x, right? Now, then you can just take in if you want to minimize with respect to beta, then you can take in the derivative of the SSE with respect to beta, which is essentially now remember now everything is in vector form, right? A beta is a vector, okay? A beta is vector. It's a p by 1 vector. And this vector, the SSE is a scalar, beta is vector, okay? So essentially what you need to do here is you're just taking the derivative of the SSE respect to each beta, and then you form a vector again. Then in short, what you have here is just equal to, so you have in Ex transpose beta, this is equal to beta, okay? X transpose beta transpose beta x beta, this will be equal to 2 of x, I think this is x transpose x beta, okay? So this will be essentially, oh, this is, so this is just essentially is 2 minus 2x transpose y plus 2x transpose x beta equal to 0, right? Set equal to 0. So in this case, the beta estimation is just x transpose x inverse x transpose 1. Okay, so this is a form for you to solve the linear regression. Well, this is a beta hat, okay? Because then once you equal to 0, so your estimation for the beta hat for your coefficient is that form. So to solve this form, essentially what you just need to do is just 3 steps, right? Involving first, you need a matrix multiplication of x transpose x. Second, this is a matrix multiplication of x transpose y. Then you need to do the inverse of this guy, and then you multiply with x transpose y. That's then that will be. For the variance, okay, the variance of the beta hat. This is just the variance of the beta hat is just essentially which essentially is just getting from this form, because in this form what is random is y, right? Because you essentially y is for the normal, or is x transpose beta, the sigma square in, right? The y is the random variable, is multivariate normal, all of this distribution. So variance of beta hat essentially this will be equal to x transpose x inverse x x transpose x. Then you have x transpose x inverse times sigma. Well, your sigma square, this is should be inside. Okay, this should be like in the middle. But in since is just identity, it doesn't really matter. So this is just equal to x transpose x inverse sigma square. Okay, so this is just basically the what do you see? Okay, I think on Zoom they still see the correct image. Okay, but in here you just like for those who are in class, you just you have to look at the whiteboard. This is I think when they reflect it on the Zoom side, they should see the right image. Now. This is essentially what we having on the slides. So if you want to estimate a beta hat, it's x transpose x, and this thing. If you want to get the variance, is this guy. So what in both form, okay, in both estimation and the variance term, you involving the calculation of two of these things, right? So you need to have x transpose x. You need to compute that. You need to compute x transpose beta. Remember, your dimension of the x is n by p, right? So the dimension of the x transpose is p by n. So the dimension of this x transpose x, this will be p by p, right? It's a p by p. So if you are doing the if you n is say your n is in the millions, right? N is in millions. P is in the thousands in this dimension. When you having this is p by p, then this you are trying to, because after that you also need to get in the inverse of this time, right? So p is relatively small. Okay, p is relatively small. So once you getting once you calculating getting the matrix value of x transpose x, then your dimension has kind of reduced to p by p. Okay. Hopefully, there are ways to do the inverse for the large p as well. Hopefully, in most cases, this p would be like in like a few hundred in that level, and then the inverse of the like 100 by 100 matrix, or even like 500 by 500 matrix, it will not be handled by single machine. Okay, you don't need to do like parallel computing in that case. So like the weightlifting computation would be this guy. Okay, and this guy. Because your x dimension, n if it's millions, then you may not be able to hold it in the in one computer. So you need some that's like parallel computing to do that. So the whole thing is the computing. This is the x transpose x and its inverse, and computing x transpose y. Now to do that, okay, to do that. say suppose your X is very large, you cannot hold it in one computer. Then what is how we can handle it? It actually can be done pretty simply. Okay, it can be done pretty simply. You can actually, if you know the technique, you don't need to do the parallel computing. Say for example, your X is a huge matrix. Your X is a huge matrix, say like 10 million by say 100, or like 100 million by 100. This is a dimension, right? It's a big dimension. Now, your Y, of course, is also 10 million by 1 dimension, right? You can actually handle this as a regression in your laptop, okay? You don't actually need to go to the parallel computing. You can actually compute everything in your laptop. The way to do it, okay? The way to do it is, again, is essentially is also the technique called the divide and conquer. Okay, so the thing is we have a big matrix multiplication, which is X transpose. It's going to be 10, right? This matrix multiplied by this guy, which is a 10 to the 8 by 10 to the 2. So you can say each of them contains about 10 to the 10 is like 10 billion. 10 to the 9 is 1 billion, right? This is like each of them contain like 10 billion elements. You want to do the regression. Now, how do you do that? It's actually pretty simple. So because the way to do that is if you slice your X, okay? You'll see this is your X. If you slice your X to be into segments, okay, by rows. So if you slice your X by rows, okay, by each row, then here this is X1. Let's say X1. This will be N1 by P matrix. Okay, this X2 is N2 by P matrix, and this is NK by P matrix. And of course, summation is N1, N2 up to NK is all be equal to N, right? So if you size your X into these segments, then if you slice X into the segments, then you have an X transpose X. Essentially, okay, this essentially is become X1 transpose, X2 transpose up to XK transpose multiplied by X1, X2 up to XK. This will be just equal to summation J from 1 to K, X2 L from 1 to K of XL transpose X. Okay. So what you did here is, although you're having a very large the matrix multiplication, but what you can do is you can separate. You can break down this is a large matrix multiplication into a smaller the matrix, and then sum it up. That'll be it. Okay. So because remember here for each of this is for each XL transpose XL. This is also a P by P matrix, right? So you sum up P by P matrix, you end up still P by P matrix. So the trick it will be the case. So if you say you have a huge data, which is like you have your huge data set, which is large, and you only have one laptop, you want to do the linear regression. So what you can do is essentially you break this is X and the Y. Correspondingly, you have to break down the Y as well, right? Y is essentially it's a vector. You can break them into the same dimension. So you can just break your X and Y into small segments, and then you can compute the segments transpose and the XL transpose XL. You compute this transpose for each segment and then add them up, right? Add them up. That will be you will have this X transpose X. Now, then you can do the x, you can do x transpose x, you can also do x transpose y, right? And once you're having that, then you just plug it in into this formula, having hopefully, okay, hopefully your p is not that large, you can still handle by within your computer. So then you would have the estimation for beta, and you would also have this is the variance for beta. So that's this is how you handle the this is how you handle the sort of like a large scale regression. If you don't have the resource, okay, don't have the parallel computer, if it's just the laptop is all you have, you would still be able to do this regression, but you have, but then of course you will not be able to just call the function in R or function in Python, right? Because that's not going to work. Then but you can write your own program by doing this, okay? Now, this is the trick is a very simple trick, okay? So if you know how to use them, it actually this is a pretty useful technique in practice. So think about one scenario, right? This is say if you're working in a big tech company, right? Like Google, Meta, this big company, and they have a regression model is based on like a user profile, and each day, okay, in this is a company, each day the data they're generating is in the petabyte data, right? Not even petabyte, like just terabytes, like 10 terabytes or a few terabytes. Now, if you want to update your because when your model runs or you try to generating anything like when you try to making model inference, you always want to use the most recent data, right? You don't want to like today you're collecting like 10 terabyte data, you want to plug it into your model right away to make sure your model is the most recent model. So if you don't know this technique, okay, or you do say your regression model is depending on the past like 100 days. If you don't know this technique, what you're going to do is every single day you're going to run a regression model by concatenate this 100 days data together and run a big regression model, right? So that will be, but that's a that's a lot. That's a waste of the resource. This is in practice, this is called a so-called rolling window regression. Rolling window regression, basically what you do is your data is generating continuously, and you want to using the most recent data to train your model. And so what you're going to do is say this is today, you're going to using the date from 100 days before to 0 days to use this data to train your model. Once you have a new day, then what you're going to do is going to using the past 99 days to the current day. Then still you have 100 days, right? You want to using the like rolling the window to use the most recent data to train your model and getting the model update. Now the way you want to do that is because first of all your data dates cannot be too long, right? If it's too long, anything you learn, it may come from like a past data. Okay, if you say your history is going back to all the way like 10 years, anything you learn is probably, well, not probably, but it has possibility. The model learn the pattern which has happened like 10 years ago or even 5 years ago, but it doesn't reflect the current situation. Okay, so therefore the history should not be too long. And then typically people just using like a rolling window with a fixed length to train data. I'm talking about here is not really about the model fitting, but it's more about like in the future if you're doing the work, this will be the situation you're gonna face, because remember data collection is a continuous process. Okay, you are not just sitting here, you're collecting the data and then you're going to use that data forever, because every day new data generated, you want to make sure you're using new data. Now here's the situation, right? So at day 0, you're using past 100 days to train your data, and then you have in the model being trained. Next day you have 1 day of new data. 99 days they are still old. Okay, so if you don't know this trick, what you're gonna do is gonna using this 100 days again and train. But if you within this framework, right? Say for each slice, it's just representing 1 day of data. Okay, 1 day of data. So then what you need to do is you can just simply store, okay, you can just simply store the X transpose X. So now you are having day I, okay, for day I, you're gonna have in the data xi, okay, which is gonna be a large data, which will be like ni by p dimension. So what you're gonna do, you can compute this xi transpose x, also compute xi transpose y, right? You can just compute this matrix and store it there. Okay, so you compress your each day of information to be this is the xi transpose I and xi transpose y. So once you're having this, later on when you try to summarize your updated model, so your x transpose x just essentially is a summation I from 1 to say 100 xi transpose xi. Next day, when next day come, what you can do, you can just simply drop the 100 days ago, the xi transpose 100, you're adding a new piece of in there. Okay, so it all saving a lot of computation. And this can be done like continuously. This is also one of the things with like online learning. When things go very fast, this is also try to update like as data comes in, you want to update your model like continuously. This is also the technique or the trick you can do. So within this, if you know how to plug in, then this actually can help you increasing your your computation dramatically. Okay, basically you are now using probably like 1% of the computing power to finish the job. Okay, if you don't know how to do it, you have to every day you have to run 100 days of data. That's a huge waste. Even more, if you want to do some sort of like a weighting scheme, when you run the regression, say you think, or you assume the data from like the most recent days are more valuable than the days in the old data, like 100 days ago, right? So in this case, you may want to say, I want to give in the data with more recent history, higher weight, right? Higher weight, and I want to give you the days in the old times or the 100 days ago. I want to give you less weight. So in here, when you're computing this guy, you can simply plug in a weight into there. Okay, plug a weight into there. This weight you can be like just be like a heuristic weight could be like you can use in the geometric decay, or you can use in like a linear decay or whatever decay function. Okay, the function you can use in as long as it's reasonable. Okay, some reasonable decay function. Say your most recent one is day 0. You're giving weight 1 up to the 100 days ago. Then this weight is like 0.0001. It's just very small number in the decay. Okay, the decay could be linear, or it could be like more like the geometric decay. This could be, this function could be like not that important, not that accurate, because what you want to do is you want to beat the so like the equal weighting, right? Equal weighting. If your assumption is right, the more recent data can provide more the recent information, then any decay, okay, any this is a decay function should be able to give you better results than your equal fitting. Because this is also related to another question, because why do you want to fit in model, right? Fit in the model is you want to make inference, right? Because why you want to fit in a linear model, or you fit a logistic regression model, or whatever model? What's the purpose of fitting model? The purpose of fitting model is about inference. Inference is you can say inference roughly you can say is about like a prediction. Okay, is prediction. Is what you say. What the reason why I'm so stressed on the like the time series of the data. This is because once the model be fit, what you want to do, maybe you want to predict the behavior for tomorrow, right? This is behavior tomorrow. So that's particularly this is if I using the example like in the Wall Street, if you're doing using example like a trading, that example you want to know exactly, you can have better feeling, because then when you see you're working in a trading company and you build this is kind of linear, of course the linear model is very you may not just use linear model, but this is the idea is applicable. So you want to using this 0 to 100 days to build a model. You want to predict tomorrow's market movement, right? Or how the stock moves. Then that's then your most recent data will make more sense, because the market is continuous evolving, and you want to using the most recent data to predicting like the tomorrow's the market movement. So that's why when you try to build in the linear model, like instead of like what you learned before, it's a static model, doesn't change. Now your model is more like a dynamic model. Okay, your model you have the same linear model, but your model is going to evolve, change from day to day based on because the environment is changing. So in this case is although it's just although you're still using the same formula, okay? The formula is the same, okay? The formula is the same. But now you have to understand is when you try to when you have in this is a form, but behind it, okay, behind the data may be different, okay? The data is maybe different. With the data collection, the data also the data the so-called refresh list, right? Refresh list. Some data are more recent. This is going to be more closer to the behavior of tomorrow. So you may want to be thinking that this way. Okay, so this is actually people use it in practice quite often. Okay, so if you know this kind of trick, if you know recognize this can be broken down, this x times x can be broken down into this small piece, the subsegment, and each segment is just 1 day, and this 1 day you can actually put in weight onto them. You actually can do better than other people. Okay, so is this clear? Any question on this? Is okay, it should be it's a simple concept, okay? But again, what I just want to illustrate is this looks simple and straightforward, okay? But if you think about it, okay, with application, you can actually generating it's depending on how you apply it, okay? Depending on how you apply it. It could be very useful in practice, okay? Now, here I have an example. This example basically is there's actually a typo here. This would be too solid. This is okay. This example basically just essentially just describe what I said here. We're generating a X matrix. This X is 2000 by 1. This is R, by the way, this is R code, okay, but it's also like a pseudocode. Don't even if you don't know R, you can still be able to understand it. It's just treat it as sort of some kind of like a pseudocode. So first is a simulation. You're generating a matrix which is a 2000. Oh, this is actually not a typo because So what I did here is I first generating a random number 2000, okay, and then I specify to the column to be 10 and make it to be a matrix. So in this example, the x is so the x is a 200 by 10 matrix. Okay, the dimension doesn't matter because then again our program should be scalable, right? So I can use in this small scale, but you're gonna say is the whole thing can be generated, can be scaled up. Okay, then I have this is the x index. X index is what I did here is just using the column bind. So C bind means column bind. What it does is so this is the x matrix 20 by 1. This is my x. I put in index, okay, 1 2 up to like 200. Put an index of 1 to 200 to x to combine with x, and then send it to the distributing file system, okay, to DFS. This is sending to distributing file system. And then I generating a y vector, which is also random, is a 200 by 1, the become a 200 by 1 matrix. The sum function is I'm doing if you have a list or some kind of like the iterable object yy. What I'm doing here is I'm generating the key value pair with the key will be 1. I'm reducing yy by using the sum, okay, by using the sum function. So this is just basically sum up all the elements in the y. That this is essentially is a reduce function, right? So x transpose x map. This is a map function. What it does here is I have a function, then I have a xi. So xi, what I'm doing here is I just taking the I remove the first column, okay, remove the first. This is different from Python. Okay, Python -1 is you are getting the last column, right? But in R, -1 means remove the first column, because when I sending this x to the distributed file system, this would be my column 1. Okay, this is my column 1. So -1 here I remove the index from the x, so I recover the original x matrix. Now the key value pairs, I'm just doing the transpose xi transpose times xi. So that's this will be this part. Okay, so I'm doing this computation. Now xt transpose x basically is I'm doing a map reduce. The input is this guy. I'm doing a map function is using call this function. I'm reduce using a sum function and then getting the value for me. So this x transpose x here is I'm going through a map reduce. The map function, remember this is a map function, right? This is a map step. You break the x into small chunks, and then you separately you calculate their multiplication. Now they will have the same key, okay? They have the same key. So therefore, in the reduce function, all this xi transpose x, they will be attached to the same key, and then they're going to be reduced. Okay, they're going to be reduced by sum. All right, so this is so the step here is just a map reduce function. We talked before, and the computing. This is computing x transpose x, right? So this is what they does here. Then x transpose y is the same thing, right? Same thing. I am having you have an xi. Now xi here is you remove the first column of xi, you recover the original one. Now yi, okay, yi you have to use in the index. This is why the index is important, because now your xi when you send it to you have to communicate with y. You have to extract the corresponding the columns from y, right? So what you do here is just basically using the index, because the first column xi is its index. So you're using the index of the xi, and you getting recover. Okay, find the corresponding elements in the y called yi. Okay, so this is the y. This is the index, because when you break the xi, right? When you break the x, then the index go with it, right? Index go with it. So you're using this index to find the corresponding elements for the yi. Now you can do the xi transpose y, you can compute that. Now x transpose y essentially is also another map reduce the task. Then you basically call the x transpose y the map. The reduce function is the same, right? You can using the sum, you're using the sum reduce function, and then this is going to give you x transpose y. And then once you're having this, you can just solve it. Solve function in the store function in the R. This is basically the computing the x transpose x inverse x transpose y. Okay, so this is how you do it. Of course, once you're having this is a x transpose x, then calculate the variance, right? Calculate variance is simple because you already have this matrix. You just inverse it times the sigma square. That's your inverse. Okay, any question regarding to this pseudical to this? Is clear? Okay. It should be pretty straightforward. Okay. Now all these are pretty good, right? This is if everything is in closed form and you can solve it, right? We don't have any issues, right? Now I want you guys think about another problem, okay? I want you guys think about the problem is there's a chat. How can we continuous update regression when there's a lasso ridge? We cannot use the analytical solution. Oh, actually, very good question. Okay, very good question. This is actually exactly what I want to. So in the Zoom, they ask a question about the lasso ridge. If you have lasso and ridge, if you have lasso, you still can do it because lasso is you have a ridge regression. You still have the closed form because the ridge is basically L2 penalty. L1 is harder because L1 is not just about the continuous update. Okay, even you have the L1, this is exactly what I'm just wanting the question I want to ask you guys. So if you have this L1 penalty, right, y equal to x beta plus epsilon, right? So now for the L1 or the lasso regression, L1 penalty, you're trying to minimize the SSE. It's not SSE anymore, right? So you want to put in a penalty. SSE is equal to y minus x beta transpose y minus x beta. So this is usual. Now for the L1 penalty, you want to minimize. Okay, you want to minimize. This is respect to beta. So you want to do the SSE, then plus some parameter. See that this is a lambda, which is your penalty, and then you have in the beta the L1 beta. So this is just, let's say, just summation j from 1 to p of beta j absolute value. Okay. Now if you add another term, okay, this is I'm not going to explain the we will talk about. We actually have another I probably have another a few slides to explain this, but I just want you guys think about this. Is L1 penalty, L2 penalty, penalized regression or penalized the model penalization has been very popular nowadays in the modeling, right? Studies models. Now, or even machine learning. Now, if you're having this is the beta in here, okay? The beta in here, what it does, what it does is you don't want the beta to be too large, okay? You don't want the beta to be too large. The reason you don't want the beta to be too large is because in some cases, okay, your beta if it's too big, then this is first of all, if you have in this term in here, you can see when your beta is very large, then this term actually not bring it down, right? Bring it back. The reason is because sometimes if your beta is uniform, your beta can actually explode, okay, like to infinity sometimes. This is basically can prevent those things happen. When you're having this term, model-wise, okay, model-wise, people have shown it can actually help. But analytically, this will create a problem. It's now if you do the D of SSE plus this lambda beta J E beta, okay? This is no longer in the analytic form. Okay, it's no longer in analytic form. Now, my question is to you guys, okay? You can think about it. My question to you is, in this case, let's talk about continuous updating, okay? Just to see if you have a big data, you have big data. If your data is big, the data your x now is 10 to the like 8, 10 to the power of 8 by 10 to the 10 to the 2 in that size. The trick, okay, the trick we talked about in the we did in the class, well, not here, like this trick, okay, like this trick is no longer works. How are you going to handle this? Okay, how do you do the regression? I'm not asking you to come up a solution. Okay, this is not an assignment. It's just something you can think about. Okay, something you can. We will cover this in like in a few weeks. Okay, we will come back to this problem again in a few weeks. And I just want to toss it out, okay, for you guys to think about. So for the question you're asking to the in the chat, so just be patient. We will come back in like probably 3 to 4 weeks. Okay, we'll come back to this problem. So you can see even for the linear regression, okay, if it's a standard form, if it's standard form, it's okay. It seems like everything is nice. We can work it out. I mean, we talk about even you can solve the standard linear regression with just your single laptop can solve the problem. No issue, right? Now, but if you go into this is not sure I couldn't say it's non-standard, but if you slightly modify, okay, modify your target function, then all of a sudden, what the trick we talk about in here is not valid anymore. Now, I want to stress one thing. Okay, I want to make one point here. Although the linear regression, although this is a L1 penalty or lasso or ridge regression, sometimes they give a slight improvement over the standard linear model. Okay, it doesn't mean the linear model is not useful. Okay, sometimes if your speed is your goal, you can. So let's say the linear model can be say I made this up, okay? See, your L1 penalty can give you like 90% of your model accuracy. Your regular linear regression can give you about like 80% of the accuracy. Okay, I made this up. Okay. Now, does it mean this linear regression is useless? Right. So this is actually a denominator. Say this is a L1. You're gonna reprice the computation will be like 10 times computation. This is 1 times. Okay. Now, in this case, it depends. Okay, it depends. If the speed is okay, sometimes you have to separate a little bit the accuracy, right, for the speed. Okay, if your accuracy is your goal, you don't care about too much about speed or timelessness, then L1 this would be a way to go. Okay, so in the if you happen to be involving in the future, like into the in the area, like say high frequency trading, these firms, to them milliseconds is that's how the time scale you can make a difference. Okay, so in that case, if you basically if your milliseconds or the is like 1 millisecond, 2 millisecond is make a difference. You basically cannot do anything fancy. Okay, you cannot do anything complicated. All you do is just try to process information as fast as you can, and then gain a little bit of edge over other people, because time is also valuable, right? The information decay very fast. Okay, information decay fast. So if you can get in, this is using much less time to extract about 80% information from the data, rather than you spend 10 more times, then getting like a 10% of the more accuracy. Sometimes that's a game changer, because then that means you already, when the people come in, sorry, it's too late, because 80% information I already extracted. Although your model is better than mine, but you only can harvest like an extra 10%. Okay, so it depends. Okay, it depends. Don't get into the this is sort of like the mindset is the best model is the most accurate model. Okay, it's sometimes not. It depends. Okay, I couldn't say it depends. For most of your problem, if time is not essential or time is not accurate, if you can afford to take time to build your model, then most time people indeed is just go with in the most accurate one. I like to do the research. Right? If you do research, you are working with historic data anyway. You don't have this kind of urgency to build it up. So in that cases, you can take your time. But in some domain, okay, in some area, time is everything. Okay, then in that cases, you have to go within the one so like faster with faster implementation. Okay, so all right, so this is by how do you handle the big data with L1 penalty? Okay, this is sort of like my not an assignment. It's just a question I want you guys to think about. Okay, see if you can come out a way to get this done like within some reasonable way. It's okay if you cannot think of it. I don't expect you guys to come up with a solution. I just want you to think about the problem and realize how difficult it could be, even within this L1 penalty. Okay. Okay, so then the next thing I want to talk about is logistic regression and how to handle with big data. But before we move on, any question about the linear regression? Okay. Now, logistic regression. This is I kind of did a survey in the last class. So most of you probably have some experience within the logistic regression. Okay, some form of logistic regression before, but but only probably like a 10%, if I recall correctly, knows how to implement it implement the logistic regression by yourself. Now within if you want to handle big data, okay, knows how to implement it is very important, because like all of a sudden there will be you're going to find out there's no tools for you to use. Okay, if you want to handle the big data, you most likely you're gonna write your own the tools. Okay, so if you understand the so like a computation details, you know how to code it from the beginning, then this will give you some kind of advantage to work on big data problem. So before we talk about how to handle it, okay, because then I cannot just tell you, say, go to Python, then import the logistic regression that module, and then you do it. Then that's not how things works. Now what we're gonna do is I have to introduce you to the how the things been done, with a single computer, and then we can from there we can break it down to the small pieces, and then so-called divide and conquer. Right, we can divide the problem, and then to come back with a solution to handle the logistic regression. Now, for the logistic regression, we can say is here is a data structure, right? So you're gonna have in the data structure, you're gonna have the X matrix, right? Just like the same setting as the regression. You have a design matrix X, you have a response variable Y. So your X is n by p matrix. This hasn't changed yet, right? Your X is n by p matrix. Your Y is n by 1 matrix. This also hasn't changed yet. The only thing change is now the Y instead of the continuous variable y up to yn is a continuous variable. Now Y become a binary. The outcome Y now is 0, 1, 0, 1, 1, 1. It's a binary outcome. Yes or no, right? This can be categorical data. This belongs to the domain of categorical data analysis. Okay, I often said to my I taught the categorical data analysis for many years. I often told my classes categorical data analysis is one of the most useful technique you ever gonna learn, because many in reality is many things people have formulated into this binary cases, okay, or categorical cases to making the so like decisions. For example, admission, the process to get into the college or get into graduate school, okay? Underlying process may be a continuous. You can be getting you based on your resume, they may have a scoring system. But at the end, when the decision is going to be made, it's still going to be either going to be accepted or going to be declined, right? It's a binary decision, and that decision from outside is a black box, right? From like your point of view, when you apply for the grad school, you either get it declined or get it accepted, right? That's a binary decision. Okay, you didn't know what's internally what is how it look like. When you apply for the credit card, right? So you either getting accepted or getting declined, right? You getting the, or you apply in the future if you want to buy a house, you apply for the loan, you also either getting declined or you're getting accepted, right? So that's many decisions in life. Okay, it is a binary decision. Okay, it's a binary decision. So therefore, to understand the process for the binary is very important. Like in every day when you go to when you're having a app like Spotify, you have music. When they try to recommend a music to you, either gonna recommend it or they don't recommend it to you, right? It's a binary decision. It's not like I get 50% of recommendation. What is that, right? So it's as Amazon when you push some like when you do the recommendation to you, like item to you, is also a binary. So it's kind of like this is a binary outcome is everywhere in your life. Okay, it's everywhere. So in one of the most important, most simple, the simplest model to handle this is logistic regression, right? Is logistic regression. So, but logistic regression, what you need is now you have the subject 1, 2, okay, I up to n. I have this object. So you have this is n. You have this yi. We're gonna assume it's follow a binary the binomial distribution, right? This is a binomial distribution. It's gonna be 1 of pi I. Okay. So what we're gonna assume here is you're gonna assume every subject or every subject in here, you're gonna follow a binary or the Bernoulli process, okay, with just 1 because it's a 1 observation in itself. Each one of them, you're having some kind of probability, okay? Is a probability pi I. So this is a probability pi I is specific to each individual, okay, to each subject. So what do you want to do here? You want to the so-called logistical model. So you want to apply a logit function. Okay, by the way, logit function. Okay, logit function of x is just a log of x over 1 minus x. This is called logit. Okay, logit function, or like just do pi. This is So this is a logic function. Oh, let me just write it this way, equal to log of pi I over 1 minus pi I. You want to assume your pi, okay, logic pi I is related to your x, because x is your feature or the design matrix, right? Or your feature vector is related to the summation j from 1 to p of this x I j times beta j. Okay. So the logistic regression basic saying everybody, for each subject, everybody itself, you're going to have some kind of the success probability, right? The binary is a success probability, pi is a success probability. You have the pi I here is what the probability of yi equal to 1, right? This is a pi is success probability. Now, each subject will have a success probability. And necessary probability is coming to, you can describe it using this is a binomial or the Bernoulli distribution. And then what are you going to assume for the logistic regression? You're going to assume this pi I is somehow related to your features, right? Xij through this linear equation. Okay, through this linear equation. Now, it is so that's what it's about. Okay, that's what it's about logistic regression. That's how the model is described. Now, it's very important for you to recognize this is pi I. Okay, you have subscript I here. The success probability is different for each subject. Okay, it's different from subject, and that difference can be described. Okay, can be predicted. At least we assume. Okay, predicted by this by the features xi. Okay, so for example, when you apply for a loan, this is x could be like your age, right? This could be gender, could be education level, could be your income, and that could be your married or the marriage status, married or not married, and how many kids you have, and where you live, zip code, and so on, right? Those are the information who is going to determine your pi I. That behind it, because people want to make decision. Essentially, we want to estimate your probability of success, right? Like in the loan application, will be you want to estimate the probability you're going to pay back the loan on time or not, right? That's what it's about. So this information can be used to describe the pi I, okay? But this pi I is unobservable. You don't observe pi. All you observe is just this is 0, 1, 0, 1. This is binary outcome, right? That's all you observe. So so this is essentially this is what I talk about. Okay, binary response 0 and 1, and then you assume your y is followed by the binomial distribution with n pi. This is n is just assumed to be 1. Pi, this is the yi equal to pi, right? You have some explained variable x1, xp, so your model is going to be logit pi or be equal to this is the linear combination of this is your x. Now to solve this pi, okay, you solve this as a function. What we do is we construct so-called likelihood function. Okay, likelihood function. This likelihood function is just essentially is a product of I from 1 to n. In here is pi I yi 1 minus pi of ni pi minus pi I. This is wrong for the binomial with 1 with ni equal to 1, right? So this is a binomial function. So essentially, what we need to do is we want to solve this is a logistic regression is by maximize our likelihood function. Okay, maximize the function. So this is come to a concept for the maximum likelihood. This is a concept which is which people using a lot in the statistics or in the modeling. I mean, for the logistic regression, for the linear regression, we'll minimize. Remember, for the linear regression, we'll minimize the SSE, right? Minimize the sum error square. It is the same, okay? We're going to prove this is also the same to maximize the likelihood, okay, likelihood function in the linear regression is the same thing. Okay, you can also, so even for the linear regression, we didn't go out of this likelihood function framework. Now, is everybody comfortable with this likelihood function? Yes? No? Okay. So if you're not familiar with the likelihood function, okay, just view this as given. Okay, this is the the function we want to solve. Okay, but we now instead of minimize, we try to maximize it. Okay, we want to maximize this function. This is what it's about. The computing package is available. You can fit in the model. Now the fitting model is equivalent to solving this to maximize this function. Okay, is essentially the same. Now, but of course, hand calculation you cannot do it. Now the question is how do you do it with big data? Now, one thing I want to show you here. Now, although we try to maximize the function, but we try to maximize this function with respect to beta. Okay, not respect to pi I. Right? Because you can see here, although we having here is pi I listing here as this are unobservable for each pi I, but this is a pi I. Okay, so this is equal to x beta. Okay, now I'm just trying to write in the vector form. X I beta. Okay, x I beta. Xi is a vector for the feature vector for each subject. Now, the pi I, okay, in this case, it just become the exponential xi beta over 1 plus e to the xi beta. Okay. So the pi I is a function of beta, right? Because by see here, you can see pi I is a function of beta. So if you plug in, okay, if you plug in this size into this function, so likelihood function is a function of beta. Okay, it's a function of beta. So what you want to do is you want to maximize the likelihood function is respect to beta, okay, not respect to pi I. Once you solve for the beta, okay, okay, so you maximize L, you can have this beta hat. Beta does not have subject I. Okay, beta is common for everybody. Okay? Beta does not have beta is common for everybody. So once you have this beta, then you can just put in this thing back to this formula. Okay, now we're back to the formula up here. Okay, so then you can have the estimation for the pi hat. Right. So this is how the inference is done. You ask beta, and then using as beta, then you say you have an observation for the xi. Somebody new applicants comes in. You have this feature vector. You plug this formula here. You place beta within the beta hat. Now you can have a pi hat. This pi hat. Then you can have an estimation of the success probability for new observation. Right. And then using that new observation, new pi hat, then where that space, then you can make in the cutoff. Say your like 0.5 probability is the cutoff. Any score is above 0.5, you're going to be say is the success. Anything below 0.5 is going to be the failure, and that's how the logistic regression model works. Okay, so now this is essentially we talk about, right? Now let xi be xi1 up to xip be the ith setting of the p explained variable. Okay, is basically that's the explained variable for the subject I. So pi of xi is equal to this is pi I is pi of xi, right? Pi is supposed to be this pi function, but if the xi is the input, right? So pi of xi is equal to exponential of summation of this beta xj. This essentially is xi beta, okay? Over 1 plus this exponential of this term. You can do this is very easy for you to verify. Okay, from here to here. Okay, perfect. This is the So therefore, if we have Ni independent Bernoulli observations at Xi, in our case, okay, let's just assume Ni is equal to 1, because for each case of Xi, let's assume there's only one observation, okay? So let's assume this Ni is equal to 1. But with that, this is in general case, if you see the Ni is just saying, if you do have multiple observations for the Xi, right? So you say you do have in somebody with the same age, same gender, same education, same income category, like same marriage, same case, and live in the same place. You may find like a couple of people, like several the 4 or 5 people with the same exactly same the information, right? So then you will have in this is a your Ni in this case is you can just combine them, okay? You can just combine them, or you can treat them separately. This is a the inference wise actually doesn't make much difference. So but in our case, let's assume Ni is equal to 1, but in general, Ni does not have to be 1. So the N will be the total observations. Yi will be number of ones response by the Xi. So then the joint probability function for the Y1 up to Yn is proportional to the function below, right here, right here. So it's a product of I from 1 to n is a product for everybody, for every subject. And for each subject I, its density function is given by this, right? It's just pi of xi to the power of yi, 1 minus pi of xi, ni minus yi, right? So that's let me explain. Let me just explain this is this density function a little bit, okay? Because if you may feel this is kind of hard to. So that function over here essentially is a probability of yi. Okay. Now, probability yi is okay. So the probability of yi can be described is like this. If probability yi is going to be equal to pi I, if yi is equal to 1, right? Probability yi is equal to 1 minus pi I if yi is equal to 0, right? So this is a discrete for the binary Bernoulli the product. If yi equal to 1, then we're gonna have probability pi I is getting for the yi equal to 1 minus pi for y equal to 0, right? That's a binary. So to put them together, okay, then the density function essentially is just these two things together, okay? Is indeed pi I to the power of yi. It's 1 minus pi I to the power of 1 minus y. This is equivalent to the 1, right? Because when yi is equal to 1, okay, when yi is equal to 1, then this is pi I, this is 0. Therefore, anything to the power of 0 is 1. So you have to do pi I. If yi is equal to 0, so then this part is going to be 1. Then this part is going to be 1 minus pi, right? So this is basically the part you see here. This is the density function or the density function for the subject I, okay? For the subject I, for the probability y. So what you see here is just you just product is the product I from 1 to n of the density function for the subject I, right? So that's what it's about. Then you having this thing is nothing. This is what you did here is you just separate this ni term, you separate out, and then you just using the pi of xi divided by 1 minus pi, because you have 1 minus pi of x to the power of negative yi, right? The negative y you can combine within the first term. So you have in this pi I to the xi over 1 minus pi of xi to the power of yi. Then you also have the extra term here, which is this guy, okay? Which is this guy in the 1 minus pi x to the power of n. Just separate, and you reorganize the orders. Now, in this case, you can see pi xi to the 1 minus pi of xi. You can also making them to be to this term, okay, to this term. You just taking the you take the log of it and then exponential. Okay, you're taking this term here. You have the exponential. You're taking the log of this thing and take exponential. What you have is this term right here. Second term is this guy. Okay, why I want to do that? Because now if you do that, you can see the second term right here. That's your logit function. Okay, that's a logit function. So on the first term, 1 minus pi of xi is going to be equal to 1 minus 1 plus e to the power of x beta, right? Because if this is pi of xi equal to this guy, 1 minus pi xi will be just simply be this thing, right? It's the same thing. So if you plug it in, okay, if you plug in everything here, the likelihood function, log likelihood function is just the log taking the log of the likelihood function, right? It's just by its name. Log likelihood function is taking log of the likelihood function. Why we want to do that? Because usually if you want to, because we want to solve a function, we need to take in the first derivative of the function with respect to beta. In the modeling, a lot of times, okay, when you're taking the derivative with respect to log likelihood, it's much easier because when you're working with in the likelihood, this is a product, right? You know, if you're taking the derivative over the product, it's going to be very tedious. You have to do the derivative of everybody and then the one by one, right? But if you're taking the derivative of the summation, it's much easier. You just push it through, right? You push it through in the item. So that's why we usually want to work with the log likelihood. But the log likelihood and likelihood function is the same because in terms of the maximization, because log function is a monotone function, right? It's a monotone increase function. So therefore, then if you're taking the log transformation of likelihood, so the maximum point, the maximization of the likelihood function or maximizing the log likelihood is going to give you the same, same solution. Okay. So your beta maximizing the log likelihood and the beta maximum likelihood are the same. Okay. So therefore, that's why we can take the log likelihood. So the log likelihood is essentially this guy because you can take in the log, taking the log, then this is summation is become this product becomes summation, right? So you got summation of log of this guy, summation of log of this guy. Then the second term is also summation log of this guy because you have exponential. So the exponential and log they cancel out. So you're going to be summation in the second term, inside term. Now, so therefore, what you want to do is you want to take in the log likelihood. Okay, so the log likelihood is will be summation I from 1 to n. Ni is the log of this guy. The negative sign, this is because you inside here, remember here is 1 minus pi I, right? 1 minus pi is equal to what? 1 minus pi is equal to this guy. So you're taking log of this thing, you have a negative sign up front, and you leave your log with 1 plus e to the power of x beta, right? So that's this is what I have here. So the first term here is this guy. The second term will be your summation I from 1 to n. Inside it will be yi times summation j from 1 to p beta j x ij, right? Within that, okay, we can do one more simplified, well, not simplification, just one more modification is we can leave in the first term the same. I'm not going to change that. Second term, now I want to switch the order of the summation, okay? Now I'm summing up from j from 1 to p. So the I is going to move inside, so yi is going to move inside with yi. Beta j, now I can move it out because in the summation of I from, there's no j, right? J is outside. So then the second term becomes summation j from 1 to p beta j times summation of I from 1 to n yxi. So that's this is a function we want to work with, right? Want to maximize. So to solve this, we need to take in the derivative, right? So remember now we want to maximize this log likelihood The goal is maximize the log likelihood with respect to beta, right? To beta. So to solve it, we have p beta, right? We have p beta. So we want to, for each beta 1 up to beta p, we want to take the derivative of the log likelihood with respect to each beta, right? To beta a. So if you're taking this, the derivative, first order derivative, then it's actually become pretty. Then this is just calculus, right? So you can the summation 1 from 10 to n. You're pushing through the derivative inside ni. Now log of this thing to be just simply be e to the x beta divided by 1 plus e to something beta, right? So you can work out the details. This is simple. The second term here, you have summation j from 1 to p beta j, right? Now since only taking derivative with beta a, so now what you left, okay, what you left is just any term with a, so beta a left. All the rest is just 0, right? Because it doesn't contain beta a. So in the second term, taking derivative just summation I from 1 to n yi of xi, because the term related to the beta a is just yi to the xi, right? So that's this is the second term. If you look at it carefully, this guy right here, this is your pi of xi. Okay, this is your pi of xi. So therefore, the derivative can be written summation of ni xia or pi of xi plus summation of y xia, and which can be simplified as summation of xia times yi minus ni pi. Okay, so we need to set in this guy equal to 0. Right? That's this is we need to solve that. Okay, we need to solve that. So if you set in this guy equal to 0, we can solve our beta j hat. Okay, unfortunately, this equation here is not a linear equation. It's not a linear system. It's a non-linear function. It's a non-linear function, because what you really want to solve is this guy right here. This is actually the equation you want to solve, right? This is kind of, I put it down here because remember pi I here is just to show you like how everything is connected, okay? But this pi I is actually not our parameter, right? Parameter is beta. So what you want to really solve is the guy setting the guy up to here. It will give you beta j hat. But then the beta j hat is a nonlinear function. So to solving this problem, we have to go using the nonlinear system. Okay, we have to go through the numerical optimization. So in that case, we can take in the second order derivative. Okay, so if we're taking the second order derivative, this is a beta respect to like beta b. Okay, so you're taking, so this guy can take in the derivative within the beta b again. Right, this is going to give you the second order derivative. You can say now, then this is this term. You can take the second order derivative. Essentially, is just be ni xi a xi b. You can this is a division, right? So you can have in this term equal to that guy. Second term does not contain any beta, so this term is gone. So there's only one term. Now notice here, what is this guy? This is this term right here. This term right here is pi I times 1 minus pi I. Okay, so therefore, then this is the second order derivative. We can also simplify a little bit with this form. Now, by using the first order and the second order derivative, then we can using a technique or the called Newton-Raphson, okay, to numerically solve for the beta. That is so we're gonna continue that in the next class. Once you go through this is a numerical solution. Okay, we're gonna end up with pretty simple. Although the derivation seems like tedious, but eventually gonna see we can end up with a very elegant solution. Okay, very elegant solution, and that solution it can be essentially is this guy right here. Okay, that solution we can use it for the so like the big data or the parallel computing, right, to solve the big data problem.
Okay, so that's all for today. I'll see you guys on Wednesday.